In this lesson, we are going to be introduced to what a limit is. So this is our definition of a limit. This is also in our yellow textbook. So it says, if f of x becomes arbitrarily close to the unique number L as x approaches c from either side, then we can say that the limit of f of x as x approaches c is L. And it's written in this form right here. So we see the limit, LIM, and we see the x with the arrow pointing to c of our function, and we get L. I want you to kind of think of it as c is kind of like your input. So if you're looking at a graph, where's it going? And then L is almost like your output. Okay, so if you think about it in terms of this way, sometimes limits can be a little easier. Okay. But let's understand kind of, let's put it into a picture, okay? So if we're taking a look at this picture, right, where of my graph f of x, and I'm going to write down the limit as x approaches 2 of my function f of x. So I want to know, what is this actually equal to? So notice that we have arrows, and we have arrows from our left side, and we have arrows from the right side, okay? And as I'm approaching, so again, I want you to think of the arrows. It's almost as if you put your fingers up and we are trying to get them to touch. Are they going to touch? And if they are, where? So again, from the left-hand side, I'm coming down. My outputs, as I get closer and closer to the number 2 for x, my outputs are getting smaller and smaller and smaller to the number 4. And same thing from the right-hand side. As my x's are getting closer and closer to 2 this way, my outputs are growing and getting closer and closer, it looks like, to the number 4. So what I get to say is that, again, the limit of my function as x is approaching 2, the answer would just be 4. Okay. Now, I also want you to point out, or I want you to recognize that the point 2 comma 4 has a hole in it, right? This is a hole in our graph. So technically, the point doesn't exist, right? D and E doesn't exist, but our limit can exist at that point. Again, from the right side and the left side, we are approaching basically the same output. So does this always happen? So let's take a look at another graph, right? What happens if I have something that looks like this? I say the limit as x is approaching the number 1. And we'll call this whole function g of x, right? So we'll put a g of x symbol here. So where is my number 1? So on this one, I'm just going to draw a little dashed line so we can kind of see what's happening here. Okay, so I want to approach 1 from the left-hand side. So as I approach it from the left-hand side, notice that I'm getting closer and closer to the output of -1. So from the left-hand side, I get -1. From the right-hand side, again, I'm going down and down and down, but notice that it's kind of ending right about there. So it looks like from the right-hand side, I'm approaching 0. So approaching -1, approaching 0, notice those aren't the same numbers. So it's almost as if our fingers cannot cross. So this means that we can say our limit does not exist at this point, right? So it's just one type of problem. Let's take a look at another using the same graph. So what happens if I say the limit of the function as it approaches -1? So let's take a look at -1. Let me change my highlighting color up a little bit. So here's -1. Boom, boom, boom. So again, what's happening? So as I come from the left-hand side, I'm going down, and from the right-hand side, I'm also going down. So eventually it will look like from the left-hand side, it looks like I'm approaching 1. And from the right-hand side, again, it looks like I'm approaching 1. So it's safe to say that this graph, when I approach -1, I will have a limit. And the answer, oops, I don't know why I wrote -1. Sorry, take away that negative, will be a positive 1. Okay, so that's one of the ways that we can look at a graph and kind of figure out what's happening. Okay, now sometimes we don't have a graph, sometimes we just have an equation, and we can create a table. So how can I use a table to estimate numerically what's happening? So let's take a look at two examples. Right? So here's our first one. So use a table to estimate numerically this limit. Okay, so we say the limit as x approaches 3 of 5x minus 3. So notice the table given. So we have the number 3 kind of in the middle, and my numbers are 2.9, 2.99, 2.999. So I'm getting closer and closer to 3, and then 3.1, 3.01, 3.001. Again, I'm getting closer and closer to the number 3. So what we want to do is we want to use our calculator to kind of figure out what my answers are in my table. So I'm going to go ahead and just start typing some stuff in. So 5 times 2.9 minus 3, so I'll get 11.5. So go ahead and write that down. And then I'll say 5 times 2.99 minus 3, so 11.95, and then I'll do it one more time, 2.39, and then minus 3. So notice that your answer is getting closer and closer. It looks like to the number 12 going this direction, right? So let's see what happens if we look in the other numbers. So, 5 times 3.1 minus 3, so 12.5, 3.0 times 5 minus 3, so 12.05, and then 5 times 3.001. minus 3. So 12.5, 12.05, and 12.005. So again, it looks like as my blue numbers are getting, again, closer and closer to the number 12. So it looks like these should be approaching the same number. So how can it be 100% for sure using, again, our table to estimate? What I can do is I can take our last numbers. So I'm going to take 11.995, and I'm going to add that with the 12.005, and I'm going to find the middle, right? So if I divide that by 2, I'm going to get the middle to be 12. So again, I'm using my table to estimate that this limit is probably equal to the number 12. Now, you might be asking yourself, well, why didn't we just plug in the number 3? I'm so glad that you asked yourself that. That's actually called direct substitution. So you can directly substitute it in and see if you get an answer. So 5 times 3 minus 3, so 15 minus 3, and notice that we also get the number 12, right? So we can use direct substitution. We don't want to necessarily always rely on that if it asks for a table, because there are some cases where the direct substitution is not going to work. But with that, we can use to kind of verify. So let's try another table. Okay. So again, let's try direct substitution right away. So we want limit as x approaching -1 of x plus 1, and then x squared minus x minus 2. So you can kind of see the numbers that I want us to use as we get closer and closer to -1. But let's use direct substitution. I'll just say ds for direct substitution, and let's see what happens. So minus -1 minus 2. So in the numerator, I'm going to get 0. And then in my denominator, I'm going to get 1 plus 1 minus 2, which also gives you 0 over 0. So this gives us a number that is an error. If we were to plug that into our calculator, it's an indeterminate form, so to speak, so it doesn't help us. So I'm just going to write error for right now. Okay. So I have to use my table because I don't have any other method to figure out what's happening. So let me plug in some numbers. So negative 1.1, and then plus 1, and then divide by, open my parentheses. Oops, minus 2. All right, so we get negative 0.3225. So negative 0.3225. All right, so if I wanted to continue to plug in the same numbers, right, and I would just start plugging in a negative 1.01, negative 1.001, because I don't want to bore you with using a calculator, you should get the same numbers as I'm about to plug in. And again, I'm just rounding it to the first four numbers. So you should get about negative 0.3322, and then you'll get negative 0.3332, okay? So what's going to happen if I use my 0.9? So let's go ahead and do the 0.9s. So if we get 0.9s and we plugged it into our calculator, you're going to get these answers. So negative 0.3448, negative 0.3344, and negative 0.3334. Okay, so again, all of my numbers seem to be negative, so that's good. They all have about 0.333 in them. So again, it's safe to say that you're probably going to connect. And again, I'm going to take the negative 0.3332, and I'm going to add that with negative 0.3334. I'm going to divide that by 2. And I'm going to get about negative 0.3333. That makes sense, right? That kind of falls in between these numbers, right? So that is going to be what my table is about. Now, what does negative 0.333 kind of remind you of, right? Hopefully what it reminds you of is 0.3 with a bar over it, which is the same thing as a negative 1/3. So again, we'll talk about in another class period how we can actually get that as a fraction instead of just a rough estimate of what we're supposed to do. Okay, so now that we've seen some tables, let's kind of look at behaviors of graphs that are limits that don't exist. So these are 3 scenarios where limits are not going to exist. Again, this is in your book, so you don't necessarily have to copy this down. So it says the limit of f of x as our x approaches c does not exist if one of these functions is true. So the first one that it says is if f of x approaches a different number from the right side and as the left side. So we've actually seen this type of problem, right, in our first example, or sorry, I should say second example. So when we approach that green line, so we're approaching from the right side and the left side. So one side gave us -1, one side gave us 0. So this example for number 1, where it approaches a number from one side and to the other, right, is one limit that does not exist. So an example of this graph, so that way we can have a clear understanding, would look something like this, where you have kind of a jump in your graph. Okay, so again, going from the right side, going from the left side, there is that break in our graph. All right, so the second one we have never seen before, right? It says f of x increases or decreases without bound. So basically what this means is that it's just getting, so it gets larger and larger, or we can say smaller and smaller, so smaller or smaller, and without bounds. So again, it's approaching that infinity or negative infinity, and so you just don't know where your graph is headed to, right? So is it approaching an actual number? No, it's not. So what this kind of looks like is it looks like it kind of blows up, right? So again, one side of our graph is going up and the other side of our graph just keeps going up. So again, none of the arrows will ever meet each other since they're facing the same direction. Okay. So again, we usually see this if we have a vertical asymptote in the middle of our graph. So we've seen that with rational graphs and stuff like that. Now the third one means that it oscillates between 2 fixed values. And basically what oscillation means is that you're just going back and forth between 2 values. So for instance, if you made a table of points and as your numbers get closer and closer to something, maybe your outputs are bouncing back and forth between, say, a +1, -1, +1, -1. So if it keeps bouncing back and forth between these two, it's oscillating, which means you're never really getting closer and closer to a specific number. So the graph of this looks something like that, where it almost looks like a sound wave, right? So just again keeps going back and forth between the two. So those are just some ideas of how something can be non-existent in our limits. Again, discontinuity, there's a jump, things going straight up or straight down. Again, decreasing or increasing without bound, or AKA going to infinity or negative infinity. And then the final one, oscillation between the two. Again, what's written in blue is in your textbook. These three graphs are not. So now that we've kind of figured out where things are where they do not exist. We've seen the numbers using our tables. We can look at a graph. We can also just do direct substitution. So the last two things are things you don't need to copy down because again, they're in your textbook and you can take a look. These are just some basic limits that they fall into. So again, B and C are just real numbers. So example number 1 where it says the limit as x approaches C of the letter B. So again, if that's just a number, right? So this would just be kind of a horizontal line, right? So again, as x approaches, let's just pick the number 2, right? Again, from the right side and the left side, it looks like our output will always be whatever it is, right? When it's straight like number 2, all you're doing is you're taking that C value, plugging in for x. Again, number 3 has an exponent. So again, you're plugging your C value in, and again, it's any number. And then same thing on number 4. The only difference is on number 4, we want to make sure that our C value is greater than 0 when our n is even, because then we don't have to worry about imaginary numbers. Okay. So how can I use these with direct substitution? So we just have a few examples. All right, it's pretty straightforward, right? So direct substitution literally means you're directly substituting into our limit expression. Okay. So if I look at number 1, it says the limit as x approaches 4 of x squared. All you're doing is you're saying 4 squared. So what is 4 squared? 16. Okay, you can kind of do these in your head for some of them. For number 2, the limit as x approaches negative 3 of 5x. So again, try pausing the video and answering this question. All right, so if you paused it and tried it, hopefully you just multiplied the 5 and the negative 3 together to give you negative 15. So again, not that challenging. Again, try pausing the video, trying 3 and 4. All right, so if we tried 3, let's do that one first. So again, this will just be tangent of pi over pi. Now, hopefully you simplify tangent of pi. So again, it's been a while since we've seen a little bit of trig, but here's our unit circle. Pi is on your x-axis, the same thing as 180. So this point is 0, not 0. Switch my numbers around. This point would be 1 comma, negative 1 comma 0. So tangent is made up of the y over x, so 0 over negative 1. So this would just be 0 over pi, which ultimately will give you 0. All right, and last but not least, number 4, the limit as x approaches 2 of the log base 4 of x. So we're just saying 4 to log base 4 of 2. So you're trying to ask yourself, you have to raise 4 to the power of what number to give you 2? Well, I'm going to rewrite 4 as 2 squared, again, question mark, is equal to 2 to the power 1. So this is really 2 question mark is equal to 1. Our question mark is just 1/2. So that means that this guy is just equal to 1/2. Okay, and so again, direct substitution should be short and fast. Shouldn't require a whole lot of work, and everything should work out. If it doesn't work out, chances are you plugged in the wrong number or you did some math incorrectly. If you have any questions or concerns at all, please do not hesitate to reach out.